Welcome to this lecture on modern retinal image analysis. My name is Bart ter Haar Romeny, and I give you this lecture live from the Netherlands. I'm Emeritus Professor. I was at Eindhoven University of Technology, Department of Biomedical Engineering, and my talk is about a screening project for diabetes, which we did by analyzing retinal images. So, why is the retina involved in diabetes? There's a small movie that explains this.
Diabetic eye disease refers to a group of eye problems that can occur as a result of diabetes. Without diagnosis and treatment, diabetic eye disease can cause severe vision loss or even blindness. Diabetic retinopathy is the most common diabetic eye disease and is a leading cause of blindness in persons with diabetes. It is caused by changes in the blood vessels of the retina. The retina is the light-sensitive tissue at the back of the eye. A healthy retina is necessary for good vision. In some people with diabetic retinopathy, blood vessels of the retina may swell and leak fluid or blood. In other people with diabetes, abnormal new blood vessels grow on the surface of the retina. At first, diabetic retinopathy may not cause any changes in vision, but over time, diabetic retinopathy can get worse. At first, a person might see spots floating in their vision, or may notice a general blurring of vision. Eventually, diabetic retinopathy may cause vision loss and even blindness.
It's quite serious, and especially in China and India, it is really alarming. And when we started this project in 2013, the rate was 11.6% in China, and it is continuously going up, and there is no leveling of this curve yet. So we were asked for help by a large group of ophthalmologists in China. Eindhoven University, can you help us to set up a screening program? And that's what we did. The project was called the Retina Check. Well, if you start looking at the retina, you can make pictures of the retina, and you see the camera on the lower right, at pretty high resolution. And these images show a lot, 20 megapixels, they show a lot about blood vessels, possible leakage, deposits, fatty tissue, etc. And the target was to screen the elder half of Liaoning province in northeast China, which incorporated 24 million people. And of course, for such a large screening programs, there were not enough doctors, so there was a need for computer-aided diagnosis. And this system had to be quite simple. It would have been a referral or no referral. And because blood vessels start to leak, we focused a lot on the analysis of blood vessels. This is a very serious diabetic retinopathy patient. And of course, you don't need a computer system to see what's wrong here, but very subtle changes are very difficult to see, and that's what we were focusing on. We started the project, the retina screening project, with many partners. Eindhoven University had the lead, and our immediately to the right, Geshi Eye Care Systems was the clinical partner. It all took place in Shenyang, in northeast China. It's a big city, 12 million people. And our university had a school there, a biomedical engineering school. And from that school, we used the students. That school was located in the neighborhood of this conglomerate of eye hospitals. We set up 2 teams in the Netherlands and in China. We collaborated with a medical company, Newsoft, Shenzhen Hospital, a large hospital in Shenyang, 3,000 beds, Ioptics, a company that makes dedicated low-cost laser scanning retina cameras, and Maastricht University in the Netherlands, who had set up a large program to study all effects of diabetes. Well, fundus images are easy to make with a fundus camera. You have 2 types, a laser scan camera or an optical camera. The optical camera, of course, and a laser scanner, they have to supply light because there's no light coming out of the retina, so after a small flash, you get a quite high resolution image of the large retina. And this is how it looks like. In the center is the macula with the fovea. We have the optic disc and all the arteries and the veins. It's incredibly cheap to make images with a fundus camera. Think about a cent per image. And if you make millions of these images, this is, of course, a serious concern. It's easy to make. They are available all over the place, and we had them available in optometry centers, in eye hospitals. They are with general practitioners. The resolution is very high, and the retina is quite special. The retina is brain tissue. So the retina has a blood-brain barrier, and in such a sense you also look directly at neurodegenerative effects. Well, diabetic retinopathy does a lot. It is the main cause of blindness. Finally, 4% of people who let diabetic retinopathy untreated, they go blind. And all kinds of things emerge. Things with the vessels, the leakage, you can have microbleeds, you get all kinds of spots that look like cotton wool, exudates, changes in the optic discs. We started the program to finally look at all these details in the retina in a quantitative way. So modern computer vision to really understand what happens. And here you see a normal fundus. You clearly see all the vessels, and this is diabetic retinopathy fundus. But how to quantify all these different features that we see? Because we started in 2013, it was a pioneering study in those days, and we learned a lot. And I'll go tell you a little bit about the journey, what we did. And of course, first you need to know what are important parameters. So you need a lot of ophthalmologist input. How to set up a screening in China, where everything is in Chinese. There's different cultural differences, different treatments in hospitals. How do you get enough data? How do we clinically evaluate and validate the results that we get? And can we interpret the findings in terms of how valid are they for doing the diagnosis? So we first decided to focus on computer vision, really understanding what do we see in terms of tortuosity, width, branching, lots of details of the vessels, and then later on put all this in a deep learning program. Here you see a couple of the approaches that we took. First, we need to know where are the vessels exactly. Can we do a proper tracking and segmentation? Can we find microaneurysms? Can we define the tortuosity or the curvature? It turns out that if vessels become weak or sloppy, that they become more curved. Can you show something about the filling degree? How much does a vessel pattern fill up the retina? That's expressed in the fractal dimension. Bifurcations. Normally, vessels, if there's bifurcation, it's 90 degrees, but if it's weak, it becomes another angle. Can we use these crossings and bifurcations to do image stitching to the right, so make larger images? So these are landmarks to couple these images together in a large panorama view. Can we find the ratios of arteries and veins and the diameters? So here's the final project layout. To the left, we start with the retinal image. We extract the vasculature, the background, and the optic nerve, and we determine a whole set of geometric features: curvature, diameter, the caliber, bifurcation, geometry, etc., microaneurysms. And finally, we have the severity grading into 4 classes. It took us a lot of work to get everything together. You need finances, you need to have a contract, you need to have a project plan, and we were very happy to get good support from the Dutch government, from China. Here you see me signing to the left with Professor Ge, the clinical head of the ophthalmology group, our contract. The minister of the Netherlands is standing behind us, Minister Bussemaker, and to the right there's another minister from healthcare, Mr. Schippers. We discussed the project in China. It takes a lot of preparation to explain what we're going to do with the clinical partners. This is me giving lectures in the Chinese diabetes department. We made a dedicated acquisition room to study thousands of in-house patients. And from those patients, we not only took those who are diabetes patients, in-clinic diabetes patients, we did not only take the retinal scans, but we also knew from the hospital information system their whole medical records and also their lifestyle, how much they smoke, they drink, etc. But also which medicine they took. This was all done in the Shenzhen hospital, 17 image biomarkers and 50 metadata, and we did a quite extensive statistical analysis. I will talk about that later. That was on patients to validate, and we also did, of course, the image acquisition of normal people, and that was done by people who came into the university hospital, non-diabetes related, but people were asked, can we take a screening picture? And if you got a couple of glasses, you went to an optometry store, and in 40 optometry stores we had cameras installed, all connected to the cloud, and we could take images from there of regular people. You see the pipeline. It's quite detailed. In upper left, you see the image coming in, and then we do a lot of phases step by step to extract vessels and do all kind of analysis, and I go take you through these steps. The image is not normally homogeneously illuminated. This is a laser scan. Sometimes you have some darker and some lighter areas, and we first started to make the images homogeneous, so you remove the inhomogeneous lighting. We did a lot of denoising because you don't want to have too much laser light on the retina, so it is limited, and that makes it noisy. And you see to the right that with elongated filters, which are elongated along the direction of the vessels, we could substantially reduce the noise in the background, but keep the vessels. We did some blind deconvolution in collaboration with Tel Aviv University. And on the upper image, you see the original image. It's a little bit blurry, but you can defocus the image, remove the deblurring, and then you can also see the nerve patterns, because all the rods and cones bring the nerves, of course, to the optic nerve, and now you can see them in this sharpened image. The arterial-venous ratio is important to see what is the relation between arteries and veins. The arteries and veins have different brightness because they have different oxygenation. Arteries are generally brighter, and if you look at the color spectrum, you can discriminate them. And we carefully did all the images and analysis of where are the veins and where are the arteries. And it turns out that the veins are more sensitive for disease than the arteries. The arteries are stronger, thicker vessel walls. So finally we focused more on the veins of the images. Detection of crossings and bifurcations as landmarks, but also to see if you cross the street, for example, you take a 90-degree angle because you want to reach the opposite side as fast as possible. The same these vessels do. They want to bring the blood as fast as possible to the location. But if there is disease, these angles, they change. We had rotating filters, and in every pixel, and if you have in a pixel 3 maxima, you're on a bifurcation. If you find 4 maxima, you're on a crossing. And that was a very easy, straightforward way to find them. And finally, we could do then an easy stitching where you could combine 9 images into a much larger overview image, which is of course important in the screening program where you want to see the whole retina. We managed to get a fully automatic microaneurysm detection by a very dedicated blob detection. And here you see the probability to the right of the detected very tiny aneurysms, so it's very tiny bubbles in the blood vessels. And the brightness of the green circles indicates the probability of with which we could detect these microaneurysms. If you have blood vessels, we could use the technique of in-painting. And in-painting means that you can remove structures. With AI, you can do it now today. That's a very similar technique. And here you see how we remove the blood vessels, and we don't replace them by a blank area, but we replace them by the same statistics as the surround. And it turns out if you remove the blood vessels, it's much better to do a background analysis than with the vessels. These oriented filters were nice. We could also look at radial patterns. So to the lower right, you see a radial pattern of all the blood vessels leaving the optic disc. And if you take a tangential pattern to the lower left, a radial pattern, concentric circles, it was a very nice technique to find circular patterns like the optic disc. Of course, we have cameras of all different types in the different optometry centers, the different hospitals. So we compared the output of all our programs with 6 different cameras. An Indian camera, Canon camera, Nidec, Spectralis, cheap and high quality cameras, and it turns out that more or less all of them gave the same results. And finally we opted for the iOptics Easy Scan because it was one of our partners and they were a very high resolution laser scan for an attractive price. Vessel tracking had different challenges because if you have vessels that are closely parallel, it's difficult to stay on the same vessel. But we had a very nice looking forward technique in which you could say, okay, I have elongated vessels that look in a very narrow area forward. And in this way we could easily deal with crossings and parallel vessels that were nicely parallel, closely parallel. When it comes to vessel width, because we have such an incredible resolution, 4000 by 3000 pixels, sometimes 4000 by 5000 pixels, we could make this resolution to micrometer accurate. So at selected points of the vessel, we had active shape models where the computer automatically constricted an area to the vessel boundaries, and then we could very nicely see this is 71 micrometer. And we could easily and fast do the statistics of these vessel width on our thousands of images. Well, vessel segmentation, you need to find the vessels. We have soft segmentation to the right and hard segmentation to the right. And if you look at tortuosity to the right, you see very tortuous vessels, vessels with high curvature. This is easily to see with the naked eye. Well, tortuosity is a scale from -0 to plus. 0 tortuosity means it's a straight line, and minus means it's convex, and plus means it's concave. So here we see to the left the measurements that we did. Every point on a vessel has a certain curvature. So we have lots and lots of curvature points. And you see the color indicates the curvature. Red means a very high curvature. And you see the histogram below, we have positive and negative. And in the middle is blue, there are straight areas. We did it again with our rotating filter technique. And in the blocks in the lower right, you see that the images from a data set, 1200 images on Messidor, the healthy have a lower curvature and the DR have a high curvature. And this was very prominent. So this turns out to be a very first quality factor on detecting does the patient have diabetic retinopathy. So vessel tortuosity turned out to be a key value. Well, we had the clinical validation with our in-house patients in Shenyang, but also in the Netherlands there was a large study going on. It's actually the world's largest multidisciplinary population study to diabetes 2, with 8,000 normals and 2,000 diabetes. They study everything from MR scans, blood investigations, and full optometry investigations, ophthalmological investigations. And we could have access to their data. That was fantastic. And in Shenyang Hospital, we were in the clinic, and every patient signed a form for informed consent, and we got these 2 data sets. And of course, we could nicely do the statistical analysis on how is the tortuosity related to all kinds of other effects related to the progress of diabetic retinopathy. And you see a couple of papers that we published here. And in most cases, the retinal vascular tortuosity was a key figure. We made a workstation for the ophthalmologists to easily work with it, and this was a research station in the beginning, and we could do a lot with this. I'll show you quickly what we could do. Here we see the different deposits that were from a leaky blood vessel. If the leaked blood is absorbed, we have all kinds of calcium and fatty deposits left over, and we could quantify them, and you could nicely see them. We could analyze the blood vessel patterns, bifurcations and crossings. We could analyze the optic disc. We could analyze the arteries and the veins separately. Here we have the arteries and the vein curvature separately. Then we went to deep learning. And deep learning, as you know, is deep because it is a neural network with many layers. And here you see a very tiny neural network with some hidden layers. And in the beginning, you detect very simple things like edges. Then you make more combinations, fancy combinations of these edges and lines. You get noses and eyes and ears, and then you get these combined into faces, etc. And that incremental context is the analysis what the deep neural network does. It's pretty much related to the layers that we see in our visual system. To the right, we have the visual system in the back of our head. We have V1, V2, V3, V4, lots of layers which do very similar analysis as we see in our artificial neural networks. Well, why is it called neural networks? Because it's related to the models of a neuron, and we have these synapses. As you know, synapses are the connection from one neuron to another one, and if you learn, these synapses physically grow. If you forget, they physically disappear even. And these size of these synapses is related to the weights in neural networks. So if an input gets stronger by growing synapse, you increase the weight in an artificial neuron. A neuron has also a threshold, so we see after the sigma, that's a summation of all the inputs, you see a threshold, and then the output of the neuron is measured. We used to have neural networks already for a long time, and it was mostly 3 layers, and they never really worked. So 75%, that was it about. But then we get multiple layers, and in 2012 there was a big hit because there was a competition every year, ImageNet Challenge. Can you properly classify 1.4 million images into 1,000 classes? And he made a step of about 12%. It was an incredible big step. Today we are on 94%. And what happens is that you put in an image to the left, you process it through all these network layers, but you don't know what are all these connections. So in the beginning, they're quite random. So first you put one image in, and you look at what's the output, and you see, hey, there's a small error. Well, then you adjust all the weights until the error is 0. And you continuously do that each time, one by one by one. And because we sometimes have hundreds of millions of connections in a neuron, you have to have big data to update all these connections before it does the proper recognition. Well, we employed deep residual networks. These are networks with a specific feedback loop, and we were quite successful in applying these networks. They are concatenations of specific blocks, and we trained these blocks with all the images that we acquired from our screening program. And we managed to get fully automatic exudate detection. What means fully automatic? That we don't have to indicate exactly where are all the pixels that have an exucate location. We only have to indicate this particular retinal image to the right has exudates, and the system then gives where they are. So here we see an image based in, but pixel based out, and it was fast. We, of course, did some nice validation study. How good is it? And to all sets of clinical databases, you have these publicly available databases, EHB, TR2, DiaRedDB. We got 96 to 99% good classification, which is really nice. You could even learn the system, if you know where the curvature is, that the AI system could indicate where are the locations with high curvature. And this was pretty nice. So now we don't have to do any computer vision technique anymore. The system learns this computer vision technique by finding the high curvature. And because curvature is such an important marker for diabetic retinopathy, this is a very promising new input for AI. There was a big challenge by the Kaggle competitions. And in 2015, there was diabetic retinopathy detection. 660 teams participated. We were one of them. There was a big fee for a prize, $100,000. And we ended up at the 17th location. That was not too bad. That's in the top 2.6%. Well, how is it rolled out? The system lasted for about 6 years. And finally, it has been rolled out in Shenyang. It all connected to telemedicine system. To the right, you see one of these vision stores. I'm sitting in as a patient in one of these cameras. We constructed the WeChat app so the patients could see the results of their images and the advice that was given by the system. And in development currently is a dedicated camera where the flash is a circular pattern around the optic center of the lens to do it with a smartphone acquisition so people can even do it at home. We managed to publish a lot of publications, over 50. We had 4 PhD students and a postdoc. PhD students have now finished their project, and this Retina Check project was converted into a TUE startup in 2017, and it was fully acquired, including all the software, by the He Vision group in Shenyang. And they are now rolling it out in a Chinese environment, and we were very happy that this happened, so all our efforts in setting up this software is now rolling out in this large Retina Check project. So here I end my lecture. I acknowledge all the partners that participated in this fascinating project. We traveled a lot back and forth. We became good friends. It had a team in Eindhoven and a team in Shenyang. So I hope to have told you a little bit about what can modern computer vision do, what can modern AI do, and how is it to set up an international project. Of course, AI continues to go on. There is much more than diabetic retinopathy now being found in the retinal images. It's a rich source, and even Alzheimer and Parkinson's disease have early indications in these retinal imaging, and AI is such a good recognizer that there's a lot of promise right here. Thank you very much. I end here, and in my conclusion, it now ends in a lot of support for the local population, especially in China, all our techniques for curvature and detection in the images. We thank the clinical patients who contributed to these validations, thousands of them, and it's all part of a Vision for Vision program. We're learning from visual, let's say, from our visual perception techniques for vision assistance, and it was part of the Vision 2022, the Right to Sight Prevention of Blindness program. So I also thank all the members of the Retina team, both in Eindhoven and in Shenyang. And I thank you for attending. Thank you very much.